Have you ever wondered how infrared air-to-air missiles actually work? In War Thunder, it's simple. Line up the reticle with your target, press the launch button, and off it goes. But how does the missile know what it's seeing? Let's find out. Let's start with the seeker head. Inside the dome is a complex system of lenses, mirrors, servo drives, and the most important component, a sensitive detector, often called a photocell. Early missiles had just one detector, made from lead sulfide. Its sensitivity range corresponded to objects at roughly 500 to 800 Kelvin. This means it could only track the hottest parts of an aircraft, like the engine exhaust, and only from the rear hemisphere. Later on, engineers learned to extend that sensitivity to lower temperatures by cooling the detector or using different materials, such as indium antimonide. As technology improved, seekers became capable of locking on to the exhaust plume itself, or even the airframe when it's heated by aerodynamic friction. That's how all-aspect infrared missiles were born. Now that we know how a target is detected, how does the missile track it during flight? The key lies in a small rotating disc placed in front of the detector. This disc serves several roles. It helps determine the target's direction, measures its deviation from the optical axis, and separates it from the background IR radiation. To do this, the disc carries a special pattern made up of alternating transparent and opaque segments. Think of them as fine slits. As the disc spins, it periodically blocks and unblocks the target's infrared signal. By analyzing the frequency and amplitude of the detector's response, the guidance system figures out where the target is and distinguishes it from the background. This simple technique, known as spin scan tracking, was revolutionary in its time. But engineers didn't stop there. The next step was conical scanning, where the seeker head precesses around the line of sight to the target. This made guidance more stable against natural background variations. However, it didn't solve the biggest issue: vulnerability to flares and infrared countermeasures. As always, new designs led to new ideas. True countermeasure, or IRCCM techniques, appeared in the next generation of missiles, with examples including the AIM-9M, the R-73, and the Stinger. One common method detects an abrupt spike in infrared intensity. An aircraft engine can't heat up that fast, so the system recognizes it as a flare. When this happens, the seeker temporarily breaks lock, allowing the flare to drift out of view. Another technique is narrowing the seeker's field of view right after launch. This greatly reduces the chance of a flare entering its sight picture. Some missiles also use dual-band seekers, which compare two infrared ranges to tell real targets from decoys even faster and more accurately. Many modern missiles combine several of these countermeasures at once, and research is still ongoing. Engineers continue to develop new coatings, focal plane arrays, and digital processing algorithms to make heat-seeking missiles even smarter and harder to fool. Did you learn something new today? Share your thoughts in the comments, and see you in our next video.